Hi everyone, and welcome to our first webinar for 2021. My name is Tom Pritchard, and I'm Principal Engineer here at LimitState and SLAB Product Manager. Today I've got the pleasure of being joined by Matthew Gilbert, who's going to talk a little bit about the technology behind the LimitState SLAB software. And today we're going to be discussing how you can use LimitState SLAB to help identify reserves of strength in existing buildings, helping to repurpose them rather than raze and start afresh. The presentation is due to last about 30 minutes, and there should be some time at the end for you to ask some questions. Hopefully in the webinar interface in front of you, you should find that there's a little question panel. If you want to ask anything at any point in time, just put them in there and we'll try and get around to a few of them at the end. If you do find you have any questions about the content of the webinar that come up afterwards, then feel free to contact us outside of the webinar via info@limitstate.com. And you can always call us as well. But without further delay, what I'll do is I'll pass you over to Matthew Gilbert, who will be speaking about the approach we took to automating yield line analysis.
Thanks very much, Tom, and thanks very much for joining us for this webinar today, everybody. And the next slide, please, Tom. And the next slide. Okay, so this is the rundown of what we're going to be covering today. So I'll provide a bit of an introduction to the problem and look at various different solutions in the next section on technology, how we can potentially get more capacity out of a slab than we might think that is present. And then Tom will basically go through a couple of examples to illustrate the methodology that we're proposing in practice, and then we'll wrap up with some summarizing comments, and then throw things open to you all for Q&A. Okay, so just a bit of sort of background to the problem. What's the case for reusing buildings? Well, we know that as of now, up to around half the total carbon associated with a building rests in the embodied carbon in the construction of the building. That's changing with operational carbon diminishing as time goes by, as we have more and more insulation, and we're switching to using renewable sources for our energy used in the buildings. So embodied carbon is a huge issue. If we refurbish and upgrade an existing building, then we typically require an order of magnitude or more less embodied carbon than if we were to demolish and rebuild. Now, historically, we as a profession and acting on the as servants of society, if you like, have very often demolished and rebuilt. We have to do things differently. The climate emergency means that business as usual isn't an option, and what we have to do is see how we can reuse buildings wherever possible. Bit of context for reinforced concrete buildings. Clearly, there's a wide range of buildings out there. Take a wide range of forms, and we're designed using a wide range of methods and codes. In the UK, we've had a number of codes, permissible stress code, and then moving on to LimitState codes in more recent years. Design methods used are various as well. So you might be looking at a reinforced concrete building that was designed using elastic permissible stress methods. You might be looking at a building that was designed actually using yield line methods or Hilberg strip method. In some of those cases, there's conservatism. If we move up to the present time, when you're actually looking at an existing building, very often elastic finite element analysis will be used. However, that's liable to give you a conservative prediction of strength. So relative to often what was actually designed and constructed, and certainly relative to the elastic finite element methods that are widely used, then there is potential for hidden reserves of strength. And the opportunity is that if we can identify hidden reserves of strength, we can maximize the adaptability of an existing reinforced concrete structure. And in many cases, we might find that we can avoid costly strengthening, upgrading works. So that's really the background. In terms of the technology that we're advocating, we're actually advocating kind of a return to the yield line analysis method. This was actually developed certainly in the sort of early part of the 20th century originally. It was used quite widely in certain countries in the middle and late 20th century. It's fallen out of fashion a little bit as we've moved to doing more and more operations using a computer. In terms of background to the method, if you're not familiar with it, it's an upper bound plastic analysis method. Simple, direct way of calculating the collapse load. So you basically postulate a mechanism and you then work out what load is required to mobilize that mechanism. And on the slide, you can see a number of different yield line patterns. The problem, or a big problem with it, is that if you choose the wrong mechanism, then you're going to overestimate the true capacity. So that's an issue. The other issue, as I mentioned, is it hasn't been computerized. It's been primarily a hand-based method, and that's where the discontinuity optimization method that's used in LimitState SLAB comes into play. So this is a systematic way of automating the traditional yield line analysis method. Relatively recent, we published the first paper on this in the Proceedings of the Royal Society in 2014. More recently, in 2017, there's been a paper published in the ASCE Journal of Structural Engineering, which covers a wide range of, practical issues that you might want to address using an analysis tool of this sort. In terms of how it works, you pose the problem as a large scale but relatively simple and easy to solve linear optimization problem. And in terms of the process, if we start off with for example, a square slab, first thing to do is to populate that slab with nodes. We interconnect those nodes with potential yield lines, and then we use optimization to find the minimum energy solution. So we find the critical yield line pattern, whatever form that might take, in a rigorous and completely automated fashion. So that's all I'm going to say. I'm going to hand over to Tom, who's hopefully going to provide a little bit more insight into how you can use this method in practice using LimitState SLAB.
Thanks, Matthew. I'm just going to take back control. Okay, so I'm going to run through a couple of examples using LimitState SLAB. One of them, as you can see, is going to be relatively basic, just get you introduced into how the software works, what it can do, and then the second one will be looking at more of a real-life situation. So the first example that we're going to look at is a basic example that's taken from Kennedy and Goodchild, and is looking at a rectangular slab with just fixed loading along the left and the bottom and simple loading along the top and the right. And in this particular case, we're looking at the simple hand calculation and what is involved in that. And we can see actually there's only one real geometrical uncertainty. This is the version, the length of beta here, in order to get to the middle of the envelope. And if I switch over to SLAB software, we can see here that I've actually got that set up. It's actually very straightforward to open a wizard. Actually, I can't do that now, but you can open a wizard and set this up within sort of 30 seconds, a minute or so. But just for the sake of speed, I've already done it here. And we can see that I've put in that postulated yield line pattern. And if I solve, we can see here we've got an adequacy factor of 1. And that's basically saying that the loading is just in sort of limiting equilibrium for the collapse mechanism, and we've got this envelope shape here, and that's all very good. This is what you might do if you were doing a hand calculation, but if I then go back to the presentation, we can see actually we have differing boundary conditions on the top and the bottom, the left and the right, and obviously that's going to affect this mechanism. So the one that we postulated isn't potentially the right one. We want to try and get closer to it, because as Matthew was saying, you've got to be looking to identify the correct collapse mechanism for the yield line method. So what we might want to do for a slightly more complex hand calculation is move the shape of this envelope, and then we suddenly go from having one geometrical uncertainty to having three, so beta 1, beta 2 and beta 3 here. If I then return to limit state slab, I can actually open a file where we've done that. We have this hand calculation postulated failure mechanism. We've kept everything else the same, so the material properties, the loading, the boundary conditions are all the same as they were in the previous one. All we've changed are these potential yield lines. If I solve, then we can see here the value that we get should be 3% lower than the original postulated hand calculated method. But again, this is more complex, and doing it by hand, we've gone from one geometrical uncertainty to three, but it's still relatively simple in terms of what we can potentially look at using yield line analysis. So if I go back to the presentation, what we're actually saying is, what is our actual critical mechanism? So we've said that's the most basic one we can think of. This is a slightly more advanced one. It's got more complicated. But realistically, what is the most complex failure mechanism that we can come up with? And if we use the software to its full capability, if I open this here, what we can see is this time I haven't said what are these yield lines. I'm letting the software determine that itself using the discontinuity layout optimization method that Matthew was talking about. If I click solve, we'll see that it fills with nodes and then works its way towards the critical failure mechanism, and that's what it's doing here. And already we can notice that it's much more complicated than even the second of the hand calculation methods that we were thinking of looking at. It's near to solving. And we can see down in the bottom left hand corner here, actually we know what the solution is going to be, and actually the adequacy factor is coming out to be 0.91. So that's saying that the original hand calculated method is almost 10% higher in terms of presumed capacity of the slab than this version here, where we've actually looked at identifying corner fans and also a far more complex mechanism, and we can animate that to see what it looks like as well. So if I go back to the presentation, we can see that the yield line method has been automated, so there's no need for us to be concerned that the critical failure pattern has been missed. We can quickly and easily check for the influence of different changes, and one of the things you might say is, okay, in Elastic, FEA could be used as an alternative for that, but in that we would need to make adjustments for column perimeters and similar. There's no redistribution of moments, and coming on from that, there's a danger of therefore under-predicting the capacity of that slab. And as Matthew alluded to, many slabs in buildings have been designed using a lot of different methods, and we want to ensure that in this day and time we're able to make the best use of the structures that are already there. So that brings me on to the second of the examples, which is taken from real life. There's a few things that have been changed to anonymize it, but essentially it's the same problem as was faced. And it's the redevelopment of an office building into residential areas, so actually an apart hotel. And the two questions that the user was looking to ask is, firstly, is the slab strong enough to resist construction loads? And secondly, what loading can the slabs take post-renovation? Is it going to be sufficient to be able to put in all the things associated with the apart hotel? And as part of the build up to doing the assessment, we're looking at doing an investigation to determine the degree of reinforcement within the slab, so we can see what type of concrete it was, and how thick that slab was, and also where the reinforcement was in it. And similarly, there's also, as we'll see in a second, a beam going through the centre of our design domain, which we also need to take into consideration. So here's just a picture of the inside of the building as it's being repurposed, and we're looking at, in this example, this sort of end part of a slab. So this corner here, we can see we've got CAD drawings and also some drawings from the site investigation that are telling us a little about what the concrete and the steel properties are. So if I go into slab again, what I can do is open it up, and we can see here we have our problem defined already. We have simple support along the top and then fixed down the side. We have a column and a beam going vertically through it. This is our cantilevering edge of the structure, and we have on the left hand side here slab properties. So we can see we've got MP values in two directions, and similarly for the beam strip down the middle, MP value is obviously a lot larger along one edge than it is on the other. And also what we have is loading on the structure, so we can open the load case manager, and the first thing we get is partial safety factors, so we can look at the details of those. And in this particular case we're applying the most modern sort of Eurocode partial safety factors, although obviously it's a building from prior to this. And also the different types of loads that we are applying. We've got self-weight loading, we've got pressure loading, and we have line loading. I'll just change that back, otherwise it's going to change the calculation. Line loading from the construction work, and also point loads from the construction work, so whether that be props or scaffolding, or also I think there's also column loading at the bottom from different floors. So we have a variety of different load types applied, and the observant amongst you will have also seen that at the top we have two load cases. So in this first load case, it's our construction load case, and we're looking at services construction, like we say, prop loads and point loads. And in load case 2, we're more worried about the overall capacity once all that's been taken away and it's in its sort of working condition. So we have things like the apart hotel, finishes, services, self-weight again of the slabs, and then just the column loading from the other floors. And we can have both of these within the same file within LimitState slab, and basically solve both of them at the same time and see which one is the most critical. So if I click OK on there, and this button here, we can actually see this is for our first load case, the positions of all the different loading that we have. So the red lines are pressure loading around the slab and the beam, green lines are obviously line loading, and then if I zoom in down to the bottom here, we can see these cerise circles, which are either associated with the scaffold that's there, or also there's ones that are associated with other columns coming in from other floors, as we say. If I then look at load case 2, you can see that's actually changed to just being pressure loading and point loading. So now what we do is just solve it, and the software will go through both of these different load cases and work out how much you need to multiply up the loading on the structure by in order to cause collapse. And bearing in mind that we've got these ULS partial safety factors already applied to it, so what we're actually saying is all we want is our adequacy factor to be above 1 in order to show that it's safe, and then we can determine if it is above 1 what that value and what that safety margin is. So we can see here in load case 1 we have an adequacy factor of 1.45, and in load case 2 we have an adequacy factor of 1.6. So if we return to the presentation, what does all that mean? So question 1, is the slab strong enough for construction loads? Well, yes, we saw that the adequacy factor was 1.45, and that means that the loading that's applied during construction needs to be increased by 45% or more in order to cause collapse under those construction loads. We can also see what the mechanism of failure is here, and it's basically sort of, this end cantilevering here and falling, going down. Second question was, what loading can the slabs take post renovation? And we saw that the adequacy factor there was about 1.6, which means that the loading there needs to be about 60% higher than we think it's going to be in order to cause collapse under these post renovation loads. So we've answered both the questions and shown that the building as it stands would be okay to A, undergo the process of renovation, and B, withstand the loading that's going to be applied post renovation. And the LimitState slab features that we used here, we had multiple loading scenarios that were present in the same file, so the construction and the post renovation. We had user-defined partial safety factors. In this particular case it was Eurocode ones, and then also we had application of pressure, line and point loading to the problem. So that brings us on to the summary. So what have we seen here? So using LimitState slab for adaptive reuse, we've quickly demonstrated the real flexural capacity of reinforced concrete slabs in existing structures. We can establish the capacity likely to reduce the amount of, and that's likely to reduce the amount of intervention that's required as a result of that. So proving that existing buildings have these reserves of strength that maybe we're not aware about, and that those can be utilised in renovation projects rather than having to knock down the building and start again from fresh. Similarly, the underlying automated yield line technology is both proven and robust, and we've hopefully shown that the software is easy to use, so you can pick it up and use it straight away without too much trouble. And there's obviously more information on the software is available on our website at limitState.com/slab. So that then gives us, I think, 5 minutes to take any questions that people may have. Like I said at the beginning, if you want to ask a question, there's a functionality in the interface hopefully that you should be able to type into. I'll give a couple of seconds for people to do that if you want, and then we'll try and get around to as many as we can during the time. Okay, I've had one question that's come through that's just said, can you consider continuous slabs? So yes, I guess we didn't show that in either of the examples, but what I can do is if I just go to a normal rectangular slab, what we can do is just remove these, so make them free, and I can add, this is mainly to show how to do it. So I can select, I've drawn a boundary in, and if I select that, and then I can set the support type to knife edge now, so we have essentially a continuous slab going over the top of this knife edge. And if I press go, so yeah, as you may expect, the yield line there is actually over that support, but you can very easily, if you want, if I turn on ortho, you can move that line different places. That's obviously going to be there, but if I move it maybe further that way, see what happens. Yeah, you can see it here, we get the sort of folding book type failure mechanism. So yeah, continuous slabs over knife edge supports are not a problem. Okay, we've got some more questions coming through. Bear with me. Okay, so we've had one. Would the use of the yield line negate the need to undertake a punching shear check? So that's something that isn't taken into consideration during the yield line analysis. So you would have to undertake that separately.
Can I just?
Oh yeah, Matthew, you can jump in.
I mean, if we had a bit more time, we could have talked more about it, but it is very much for flexural failure of slabs. It doesn't tell you anything about punching shear. It doesn't tell you anything about deformations prior to collapse either. Now, in the case of existing structures, you're in a better place in a way, because you can actually, if you're concerned about serviceability deflections, you can actually apply some load to one or more parts of your building and actually measure the deflections and see if it's reasonable. And very often you will find that the actual deflections are much lower than you might expect. I mean, partly the concrete's been there a long time, and it is whereas the clauses that are used for normal serviceability considerations typically assume 28-day strength and stiffness, and a concern about cracking of brittle finishes if they're actually constructed along with a building. Whereas clearly that isn't going to be the case here. So it does flexural failure very well. However, it's not going to deal with every possible scenario, and punching shear is one of those.
Thanks, Matthew. We had a second question, which I think that may have answered, which was, does the software take into account the deflection of the slab? Final question is, can we take into account corner uplift? Okay, yeah. So I guess probably the easiest thing to me is for me to demonstrate that again. So if I do another basic rectangular slab, and in this, actually, yeah, I could do a square one. So let's make it 4, not symmetry, simple. So this is just the wizard that sets up a basic slab for you. So I'm just setting up the 4x4 with simple supports all the way around. So you can see here, if I solve it as it stands, we'll just get simple cross failure mechanism, fails in that method. But what I can do is, if I then select the boundaries, you can see in the property editor on the right hand side here, it has an option for support lift off. If I click that to true, solve again, you'll see that the failure mechanism on plan is decidedly different. So these lines have split at the corners, and if I animate that failure mechanism, you can see here in the corners that we're getting that lift off of those. And you've not had to go through and say where that lift off starts to occur or anything like that. The software has determined that by itself. Okay, so that's brought us to 1 o'clock, so the end of the webinar. I'd just like to say thank you again to Matthew, and thank you to everybody for attending today. Obviously, we hope you found the webinar useful. If you do have any questions, then please do feel free to get in contact with us, and we'll be more than happy to answer them for you. And just as a final note, this is the first in a series of webinars for 2021, so please be on the lookout for emails and notifications, mainly I think through LinkedIn and Twitter and things like that, saying that the next one is coming up. We hope to see you at one or more of those. So again, thank you for attending, and hope to see you next time. Bye.